Thanks, everybody. I think we'll get started. All right, so it's my pleasure today to introduce Hamish Prince, who's going to be presenting the work he's done over the last 4 years, or almost 4 years here for his PhD. By giving you a little bit of background, so Hamish, as most of you know, is from New Zealand. He did his bachelor's and master's in science in Dunedin at the University of Otago. He already had a pretty extensive research background, I would say, before I met him, or before he asked to join my group. He had studied snow and ice on the Brewster Glacier, in particular with a view toward understanding the surface mass balance and the role that different storms play, as well as the different radiative processes in melting and creating snow. He also had done some work on the socioeconomic impacts of atmospheric rivers and the precipitation from them, which is very important for New Zealand. And even after we accepted him to come right before COVID hit, and so he deferred his entrance into our program for, I think it was 2 years maybe, during COVID. But he was able to also land an internship, a research internship with Scripps Institute of Oceanography. So he kept himself busy, did some other work there, different than what he did for his PhD. So he ended up joining us in September of 2021. And he's basically spent most of his time understanding polar energy balance and the role that the polar energy balance plays in atmospheric heat transport. He's now started to ask questions about how well do we even know atmospheric heat transport based on observations. And I'm just going to say a couple of things, sort of anecdotes. One, it was very convenient for me last year to have somebody from New Zealand in my research group, because as most of you I think know, the two pre-fire satellites launched from Mahia, New Zealand last May, and so Hamish was gracious enough, I would say, to schedule all kinds of visits with local universities and actually participate very actively in some outreach for the pre-fire project right around the launch down in New Zealand. And the other thing that you'll notice this, I won't even really need to tell you, but I did want to point out that Hamish won an award from, I think it was the AGU, is that right? For data visualization. And so he will have many graphics in this presentation and that will attest to why he won that award. So I'm just going to leave it there and let Hamish take it from here.
Sweet, thanks for that, Tristan. Yeah, kia ora. Good afternoon. Thank you all for coming to this. It's a pleasure to share the work I've done for my PhD over the last few years. We're very much thinking global scale energy here, so absorption, transport, and emission of energy across the entire globe. And of course, the distribution of that energy is fundamentally tied to the circulation of our atmosphere and our oceans. So that's an underlying theme across all of this work. So let's just start with, if the Earth had no atmosphere or ocean, the surface temperature is defined solely by radiative equilibrium. It's the balance between incoming solar radiation and the thermal emission. And of course, as you get towards the poles, that solar absorption reduces down. And so if we had no atmosphere or ocean, our equator would be about 70 degrees Celsius, and our poles would be around -70, -80. And that's kind of what it's like on the moon. There's no atmosphere or ocean, and that is the temperature gradient, because there is no redistribution of heat going on the moon. But we do live on a planet with an atmosphere and an ocean. And so these diffusive fluids act to reduce this temperature gradient. And so we get a profile a bit like this. The tropics are around 30 degrees Celsius, and we drop down to around -20 towards the polar regions. These diffusive fluids mix this energy around, they take a bit of the excess energy in the tropics and they send it towards the poles. Just for fun, if these fluids were perfectly diffusive, all those temperature gradients would be compensated. So you'd have the same temperature across the entire globe, but we know that's not true. These fluids are only partially diffusive, and so we end up with our profile of Earth that looks a bit like this. So this transport of energy raises temperatures in our polar regions by about 20 degrees Celsius. And of course, increasing temperature increases our thermal emission, and so the poles radiate about twice as much heat out to space than they receive from the sun. And that's getting energy from the tropics, sent poleward, and now the poles are in this deficit of energy. So the energy exchange and the poleward flow of heat defines our climate system. I've plotted two lines here. It's our top of atmosphere absorbs solar radiation profile, reduces down towards our poles, and then our outgoing thermal emission. You can see there that the solar absorption is greater than thermal emission in our poles, in our tropics, and so we have this surplus of energy, and that surplus is then fills these two deficits. The area in orange equals the area in the blue on the outside. So that's our net climate annual mean. We can show that in a bit of a different way. This is the same data, just shown vertically. We have the south pole to the north pole. Our absorbed solar is a gain of energy, and our thermal emission is a loss of energy. You sum these two together, you get your net energy. We have our surplus in the equator, and our two deficits in the pole. Now, if you take the integral of this plot from one pole to the other pole, you end up with your top of atmosphere energy transport. You have southward heat flowing through the southern hemisphere and northward heat flowing through the northern hemisphere. And now this transport's from the top of atmosphere perspective, so it's being done by both the atmosphere and the ocean. And combined, that gives us our meridional heat transport. Now let's try build some intuition here. If we put a little hat on the Earth and draw a boundary around a latitude band, the solar absorption dominates below that, and the thermal emission dominates above that. And so the first chapter of my PhD is asking the question, how is this thermal emission changing in our warming climate? We know our polar regions are undergoing some pretty substantial changes, loss of sea ice, excessively rising temperatures. So are we seeing changes in the thermal emission that is maybe changing our fundamental balance of energy from the top of the atmosphere? And this was my first paper, Tristan and I published last year, on the energetic adjustment of the Arctic and Antarctic. So here I've shown the first plot for the Arctic, and what we found is that sunlight is being absorbed more in the Arctic region. You lose sea ice, you lower your albedo, you absorb more sunlight at a rate of about 1 watt per meter squared per decade. That's about 1% per decade more increase in solar radiation over the last 20 years. But the interesting thing we found is that thermal emission is also increasing at about the same rate, 1 watt per meter squared per decade. And not only that, is that 2/3 of the variance of thermal emission is described by solar absorption within a given year. So we're finding that the thermal emission from the Arctic is responding immediately to the solar absorption. That there's this rapid compensation that if you absorb more radiation here, it warms the surface and it emits back to space. It's our classic ice albedo feedback. And so we call the Arctic the shallow bathtub, that we're not losing that energy that gets absorbed by our solar radiation, it's being emitted back to space. But in Antarctica, it's quite different. We are seeing increases in solar absorption. It's not as much as the Arctic, but especially in recent years, as we're losing sea ice around Antarctica, we are increasing more solar radiation. But we're not increasing the thermal emission at all. It's remaining dead flat. The thermal emission from the top of the atmosphere over Antarctica is not increasing over our observation record over the last 20 years. And so the region is gaining energy, and that isn't being emitted back to space. So we call it this energy sink, and it's our southern oceans really that is picking up that energy, taking it away from the surface to a place that isn't able to be emitted back to space. Let me just show that same plot that solar absorption describes very little of the thermal emission variability. That there are other things in the Antarctic atmosphere that controls the variability of thermal emission. It could be things like water vapor over the continent, or as opposed to surface ocean temperatures, which is what we see in the Arctic. So we have these two contrasting regions, but we have these other arrows on the plots, and these are our atmospheric and oceanic transports. So I showed the top of atmosphere exchange going on. In the Arctic, it's remaining balanced. In the Arctic, we're getting more absorption going on, but isn't being compensated by a thermal emission. How are these arrows, how are these other transports responding to our top of atmosphere? That's where the next question goes. So the polar deficit equals the heat transport, which must equal the equatorial surplus of energy. These three things must, in the annual mean and the time mean, they must equal each other. So if you start increasing how much energy comes out of here, it must come from somewhere else, which all must balance out at the end. So I'm interested in the atmosphere. To do the atmosphere heat transport, it takes a bit more work. We need to know both the top of atmosphere budget and our surface budget. So our top of atmosphere is our shortwave and longwave radiation. At the surface, we also have that, the absorbed sunlight and the thermal emission from the ocean. But there are these other components. It's our turbulent heat fluxes, our latent and our sensible heat. So here's our same plot on the side. The atmosphere cools radiatively. The atmosphere absorbs sunlight. That's our little orange sliver here. That's sunlight absorbed by the atmosphere. And then the atmosphere gains tremendous amounts of heat from the latent heat flux from the ocean surface. Evaporative warming of the atmosphere does a lot to add energy to the atmosphere. There's a small component of our sensible heating off the surface into the atmosphere. We sum all of this together like we did before, we get our surplus of heat and our two deficits, integrate that from pole to pole, and you end up with your atmospheric meridional heat flux. So let's come back to our Earth. Let's slice the atmosphere now. So the surplus of the atmosphere, of the energy within the atmosphere here, must go through the atmospheric heat transport and then be a deficit of energy here. Like I said, these three things must equal. In the time mean, the surplus, the deficit, and the poleward transport must equal out. We have to have energy closure. And so we could ask the question, so if more sunlight is absorbed in the tropics, does that lead to more heat transport across a latitude into the poles? Not necessarily. There's one other component that we haven't mentioned, and that's our moistatic energy. The atmosphere itself can store energy. Think of it like a sponge. So if you absorb more sunlight here, it's not immediately going to go across a latitude. It can get absorbed by the atmosphere and stored as moistatic energy. We also include kinetic energy, but that's a very small proportion compared to the other components. And so the change of energy in the atmosphere, we call the atmospheric energy tendency. And it's essentially a time derivative of the vertical integral of moistatic energy. That's just everything in the atmosphere that can add energy. It's temperature, it's moisture, it's the height of the atmosphere and any motions going on. So, more sunlight absorbed here could just increase the local moistatic energy and not result in anomalous transport. So we need to make sure we consider the tendency when we do our budget here. One little point is that the tendency reduces to zero on the annual mean with respect to the seasonal cycle and to variability. In the long term, this isn't true because we do have global warming. The atmosphere itself is increasing in temperature, but with respect to anomalies and the seasonal cycle, our tendency does reduce down to zero. Just a small point there. So the big question, as Tristan hinted at, I want to ask how well do we measure these variables? Can we produce an observational record of things going on here? I showed the Arctic energy balance to start with. How about all these other components? So in order of quality, we do measure the top of atmosphere budget really well. There's been satellites out there since the 50s. Tom Vonderhaar was just here on Monday. He could talk back to the days of Sumi here in the department, launching these broadband radiometers. We measure these two components really well. Surface radiation is a bit more tricky. You have to go through a bit of radium transfer, but we still have good observations of that. The third one is the complicated one. Observations of our global, spatially distributed turbulent heat fluxes. So, how do we observe our turbulent heat flux? The first option is through any covariance. If anyone wants to know more, you can talk to Anka about this, but it's essentially a point tower that measures the eddies going on and the vertical fluxes. But these are the best that we have, and they're not perfect, and we can't get a global perspective from these towers. There's just not enough of them around. So the alternative is to use what's called a bulk flux method. And so if you know the gradient of temperature and moisture at the surface, and you blow a wind across those, you can get your latent and sensible heat fluxes. And now there's been a bunch of satellites up there since the 80s that measure these properties, measure the surface winds, measure the surface temperatures. Many of them are these microwave radiometers and scatterometers, and they keep being launched. And so there is a good record of these properties that you can then scale by the wind and density of the atmosphere and a few other components to get these energy terms into the atmosphere. Here's just a quick schematic of how one team from Japan does this calculation. They take in wind speed and the sea surface temperatures from different estimates. They take in brightness temperatures and cold water vapor and all sorts of things to get out your turbulent heat flux. And this is a long history back into the 90s. It's a rabbit hole that I'm not going to go into, but there's been a lot of work to try and develop these kind of maps, of global, fully global maps of turbulent heat flux over the ocean surface. But historically, these calculations of surface energy have not been sufficient for climate science. There's this quote from Trenberth back in 1997 that these estimates have systematic errors arising from parameterization, sampling, and uncertainties. So everything along that process that I just described, historically in the last 20 years, has been not enough to do climate science with them. But we are almost 25 years after this, and we have ongoing and improving spaceborne observations, and so the question is, do we do these better? Do we now observe these properties that are in alignment with what should be going on? So there are two ways we can calculate atmospheric heat transport. The first, what I'll call the dynamic heat transport, which some people also call the direct, is you calculate the poleward flow of moist-static energy. You just take your moist-static energy and multiply it by your poleward wind, your V, and you can break that down, but it just gives you your heat transport. That's just calculating this directly. You have to use reanalysis for that. We cannot observe these properties across the entire atmosphere. So reanalysis has to be used to calculate direct dynamic atmospheric heat transport. The exciting part is this energetic indirect heat transport. If we account for all the other fluxes and take that integral from one pole to the other pole, we should be able to calculate this purple arrow from our observations. And so the question is, using these two estimates, can we get out the same atmospheric heat transport? So first, before I move on, what is a reanalysis? It's a magical website that gives me all the data I want. It takes our observations, which we know are imperfect. There is gaps missing, there is times missing, there are variables we don't measure. It meshes them with a physics model, does some data assimilation, and it gives us our final data. It uses physics to fill in the gaps in space and time, and it also calculates new variables. But reanalyses do not conserve energy. They often do unphysical adjustments to match different time steps and through space as well. So if we were to start to study trends in energy from reanalysis, it's a really dangerous thing to do, because we know that reanalyses don't conserve our energy. They don't exactly match reality. They're doing their best guess, and through that there's often unphysical adjustments being made. And this leads me into my second chapter here, Constraining the Atmospheric Heat Transport from Earth Energy Budget Observations. And I must say, Aaron Donohoe at the University of Washington has been an enthusiastic collaborator on this work, and so the three of us, myself, Aaron, and Tristan, have a paper that will be published imminently from this work in the Journal of Climate. Now there's one other point here that motivates this work. So here's a plot from Tyler Cox. He was a graduate student at Washington in the last few years, of total trends of heat transport from reanalysis, from global coupled climate models, and from atmospheric models as well. And you can see there's quite a bit of disagreement between them. The reanalyses suggest a lot more heat transport going poleward in the tropics versus nothing else going on in the models. So there's not agreement in the historical trends of heat transport. So wouldn't it be great if we could add a line to this plot of the observational record of heat transport? That's part of the goal that we're trying to achieve here. So here's my method. We can calculate AHT from both dynamic and energetic perspectives. So first, you can just take your reanalysis, you can download your moist-static energy, you can download your winds, and you just get heat transport from your reanalysis. You can also download your energy budget from reanalysis and get an energetic AHT solely from reanalysis. But the exciting part is when we use our observations of radiation and turbulent heat fluxes to get an energetic heat transport from observations. One point I mentioned before, we cannot calculate moist-static energy from observations, so we have to use a tendency from reanalysis. That's one aspect that does not make this entirely independent from the reanalyses. I use 5 different observations of the surface turbulent heat fluxes from NASA, from Hui, and then groups in Japan, Germany, and France. C-flux, OA flux, Jofuro, HOAPS, and IFRAMA. You might have heard of a few of those. They're used widely in all sorts of different communities, from ocean people to the atmosphere. So here is our annual mean sensible heat flux and latent heat flux. It's also the zonal mean. So when you see 0, that's across the whole equator. What is the mean sensible heat flux? You can see there's some reasonable agreement, but in the northern hemisphere, for example, the observations tend to overestimate, compared to reanalysis, how much heat is coming out of the ocean and into the atmosphere. But just look at the scales here. We know that sensible heat flux only adds a very small amount of energy to the atmosphere, versus the latent heating is where most of our energy comes from. And when we look at the reanalyses compared to the observations underestimate how much latent heating is going on. There is not agreement between products for how much evaporation occurs within our tropics. And so when you sum all of this together and you get your full energy budget, area weighted from pole to pole, you can see our surplus of energy here and our deficits here. You can see there's some quite severe underestimated total energy into the atmosphere compared to reanalyses. And so if you're a mathematician, you can do that integral in your head yourself and maybe guess what's about to happen. But when you do integrate that plot, we end up with a severely underestimated heat flux compared to reanalyses. So if you take your state-of-the-art observations of all of these fluxes, hope that they close, do the integral, you end up with a much lower number than what all the reanalyses say. I've got about 5 different lines there from different reanalyses. ERA 2, JRA, ERA 5, from a few different estimates, different groups who calculated, they all say the same thing. It's about 4.5 petawatts in the northern hemisphere mid-latitudes versus below 3 from our reanalyses. Southern hemisphere is not too bad. That gradient of energy is a bit more in alignment to the southern hemisphere, but it's really that northern hemisphere gradient from tropical evaporation and overestimated heat fluxes from the surface gives us a much lower observation. So there is still disagreement between our best guess observations and reanalyses. Here's the seasonal cycle, and the one, I'll take a little bit to describe this. Purple means northward flux, blue means southward flux, sorry, green is southward flux, and so you see it amplifies in the winter times when our storm tracks maximize, and through the southern hemisphere winter as well. That's when our poleward heat flux is strongest. And here's the ERA 5 energetic, but I want you to draw your eyes to the sea flux, so one of the observation products. You can see the summertime heat flux is where we underestimate the reanalyses the most. And so it's not across the entire year that these differences are coming from, it's mostly coming from the summertime. That summertime heat flux from observations is underestimated. Okay, we have mean state differences, but how about the variance? Here's the variance. It's a time series from 2004 to 2015, sorry. At 45 degrees north at the equator and 45 degrees south. I've averaged the observations together, I've averaged the reanalyses together, and I've taken the anomaly. So any mean state difference is now collapsed down and it's anomalous to itself. And you can see there's some quite good agreement here, that these two lines tend to follow each other. So while they differ in their mean state, the variance appears to be very close. At the end of 2007 here, you can see they both dip together at 45 north. End of 2010, they both show this extreme heat flux poleward in the northern hemisphere. And so we can calculate the correlation between these two lines, and we get a plot like this. The atmospheric heat transport correlation at every latitude. It's a bit messy, but starting with the dotted lines, that's the reanalyses. And so that's showing how related the reanalyses time series is to the ERA 5 dynamic, what we sort of consider the best guess at the moment. And so you can see here that even ERA 2 and JRA only have about a 0.9 correlation through the mid-latitude, that drops down to below 0.8. So reanalyses don't agree with each other, the variability of heat transport through the tropics. Here is our observations down here. They show the same pattern. They're less accurate of capturing that variability in the tropics, but through the mid-latitudes we get up to about a 0.8 correlation, which I'd consider pretty reasonable. We can just flip it around and do the correlation back to sea flux, so one of the observation records. You can see that the other observations tend to agree, and the reanalyses is the one that drops out. It's just the same plot in reverse. And now continuing on to finish up this chapter, here is the full time series of every latitude zonal mean from ERA 5 dynamic, the energetic, and then our two observations, sea flux and OA flux. So from this plot here, they look like they're in agreement. But when you plot it out from every latitude, you start to see some patterns going on, especially in our observation of sea flux. It looks like there's a lot more northward heat transport, or anomalously north transport, less southward transport early in the period, in both sea flux and OA flux. So there appears to be some non-stationarity, like this could even look like a trend if you squint hard enough. It was pink here, and then there's less pink further beyond here. And so is there a trend going on? If you use this record for heat transport, it looks like there might be. But if you turn to your reanalyses, there is definitely no trend going on here. So yeah, observational anomalies appear to have a non-stationarity. There is variability in the variance and the trend. So if we move on, just a quick few conclusions. Our observed surface energy budget underestimates the magnitude of tropical evaporation. And so if you calculate your atmospheric heat budget from observations, you underestimate how much heat is coming out of the oceans. Because of that, it reduces the poleward gradient of heat energy, which leads to a lower atmospheric heat transport. So we are not accurately observing our heat transport. There's still significant disagreement between calculated from reanalysis dynamics and what we can do our best guess from observations. But there is reasonable agreement in their time series, in their variability. And so that variability is what I want to dive into a bit more. So what is causing the variability in heat transport? What components of our budget give us that variability. Now, I will say that the dynamic part of this question has been addressed by many people over many years, pulling out the dry static versus moist static transport and the trends in these dynamics. Things like what happens in the tropics to send heat poleward, the meridional overturning, the role of stationary eddies in the northern hemisphere, transients in the southern hemisphere. This has been a question that's been addressed from a dynamic perspective, but with all those products before I showed you, this hasn't been addressed from this energetic perspective, especially from these new observations we have. And that leads me into my last chapter here. So looking at the energetic expression of monthly atmospheric heat transport variability. Now, that non-stationarity I showed in the observations also comes across in the reanalyses. All of these lines, so this is a time series of atmospheric heat transport at 45 north, the equator, and 45 south, all from reanalyses. These should all be the same line. They should be on top of each other. The black one is the one calculated from Era 5 fluxes, so considering the fluxes from the surface and atmosphere in Era 5 compared to the dynamic moist static energy transports. And the big difference you see here is from 1994 to 2004, there's this drift where the fluxes within Era 5 become in agreement, close to agreement, with the dynamics of Era 5. And this has been talked about before. They know that there is issues with all reanalyses going back in the energy before 2004, primarily attributed to the latent heat fluxes, but specific satellite products they know are erroneous before that time. And so this is a case where adding more observations does not actually improve your estimates. It's been discussed that individual satellite products are drawing this value lower than what it should be. Then the other point to bring up here, there is also non-stationarity in the seasonality. There's the other point, that there is disagreement with what the seasonality of the energy budget is between reanalyses. But I'm interested in the monthly anomalies. So I can remove any of these trends. I can remove the low frequency variability, and I also want to remove the seasonality, whether that's non-stationary or not. So here is my record of the original data, reanalysis atmospheric heat transport going back to 1980. And to do this, I will use a seasonal trend decomposition with a low-pass filter, STL decomposition. Now this is magical. I take that time series, I pass it through this filter, it identifies any low pass, any trend in low frequency variability with the low pass filter. It identifies a seasonality that can be seasonally varying. So you can see here that the seasonality doesn't remain the same, that it does vary over time. And you remove both of those from the time series and you end up with your monthly anomalies, which is what I want to get. So just to pull us back to where we were before, I want to ask what energy budget terms are varying to allow for changing heat. So if this pink arrow changes, there must be something changing here, and there must be something changing here. Maybe it's solely gains and losses of moist static energy. Maybe it's solely gains from solar radiation and thermal emission. We want to look at what causes monthly variability in this arrow. Causes is the wrong word. We're not identifying causality here. What is consistent with variability in the pink arrow? Because these two things, these all must balance out, but we're not talking about causality here, just what's consistent. How do we close the budget when this pink arrow changes? Again, here is the atmospheric energy budget. If you sum your radiation together, the atmosphere cools radiatively by about 100 watts per meter squared across the entire globe. This blue here is our latent heating, evaporation. You can see most of the energy in the atmosphere comes from this gain of heat from evaporation from the ocean, peaking at about 150 watts per meter squared in our tropics. You get a small bit of sensible heating there. I've split this up into different regions. So this is the same data as before, but shown for the tropics, for the mid-latitudes, and for the polar regions. And so the dashed is our loss of energy, and the clear is our gain of energy. So you can see in the tropics, the evaporation, and this is split by month as well, that's the other point. Evaporation is our primary gain of energy to the atmosphere, and our thermal emission is about half. As you go towards the poles, the thermal emission starts to dominate, and you get all of this loss of radiation. And there's very little evaporation that occurs in our polar regions, and so of course, a gain of energy from evaporation in our poles is quite low compared to the tropics. But we're interested in monthly variability. And so if you take all those months and you calculate the standard deviation for each month and plot it relative to each other, so this is just showing the size of the bar is the standard deviation relative to the other bars, that tendency has a disproportionate variance compared to something like radiation. So even though contribution to the mean state is quite low, the variability, the absolute magnitude of the variance of the tendency is quite large. And so the real way to describe it, maybe the more intuitive way, is to say that the variability in temperature in your polar regions is on a larger scale of energy than the variability of the radiation in your polar regions. That the moisture energy in your polar regions is more highly variable from year to year than the absorption of radiation, or the absorption from latent heating. Interesting. So, let's take this time series of atmospheric heat transport and regress it onto the energy budget, the zonal mean energy budget. And so what I've plotted here is the regression coefficient. So it's in terms of watts per meter squared for a 2 standard deviation anomaly across 30 degrees south. And so when you regress your energy budget onto this, of course you have to have a gain of energy on the equatorward side and your loss of energy on the poleward side. It equates to about 5 watts per meter squared increase in the zonal mean energy budget at about 5 degrees north and a loss of about -7.5 degrees south. Cool, we're close to the budget. We gain energy here, we lose energy here, energy has been sent across here. It all works out, but what we can do now is break this down into what component is causing these gains and losses. I'll let you have a think about what component might be doing that. Do we think radiation is causing this increase? This is for the monthly variability of heat transport. What varies on monthly scales that causes this gain of energy here and this loss of energy here? Let's start with radiation. Nope. Radiation does not contribute to this gain of energy associated with monthly variability of heat transport. There is a small response on the poleward side. And so of course if you warm your atmosphere here, you'll increase your thermal emission, and so that's what we're seeing here. It's an increased thermal emission when we send more heat poleward. That's pretty intuitive. But we don't see gains of radiation associated with this energy. So that could be something like changes in shortwave absorption is not associated with poleward heat transport variability. How about sensible heat? Nope, not that either. There is a negative anomaly. Again, we're seeing the atmosphere losing energy to the surface through sensible heating. Again, if you send warm air poleward, warm air is being sent poleward, it's going to warm your ocean surface anomalously. There's going to be a heat leaving the atmosphere through its sensible heat flux. But again, the surface is not warming the atmosphere. It's not providing this energy in the monthly variability. It's not that either. How about the tendency? Again, no. We see a loss of heat transport to the tendency on the poleward side, and so this is heat transport convergence, is what you can infer from that. It's an increase in the moistatic energy poleward of your heat transport anomaly, but we're not seeing a response here. If we did see a response here, it would show a divergence of heat from this part of the atmosphere, but it's not diverging moistatic energy. We do see increases in the local moistatic energy on the poleward side, but that is not what's providing the energy for monthly variability. So what could it be? There's one term left. It has to be our latent heating. It provides almost all the energy associated with poleward anomalous heat transport across city north. So the other way to describe this is that variability in tropical evaporation, so this is between 30 degrees south and 0 degrees south, variability in this is the sole describer of heat transport across this latitude. It's the variance in evaporation in our tropics, which is consistent with variability in heat transport across 30 south. It's pretty cool. Now, we have all these observations I just showed in the previous chapter. We can use those. So I've got the same plot here, 30 degrees south and 30 north, so we're showing heat transport into both mid-latitude regions. I've got the equator here, 30 north here, equator and 30 north, 30 south here. So heat is going this way. Gain and loss, gain and loss. And just a little point here. So we're gaining energy through our latent heating, so evaporation and condensation, it releases that heat into the atmosphere. but now that heat is available to be lost through our other components. And that's why we see almost an equal share through our other components. It's not gaining through latent and losing all through latent. We're gaining through condensation, releasing energy. That energy is then shifted poleward, and it can be lost through any other component. It can go to warming the moist-static energy. It can go to warming the surface through sensible heat, and it can be radiatively emitted from the atmosphere. So we're seeing this conversion from gains of latent heating and loss through other components. Here's a bunch of those observation products. We can plot the same regression, and they tend to agree, especially like OA flux and I-framer. The majority of the heat gain associated with anomalous heat transport is through our latent heating, and they all show this equal share on the poleward side. Something like C flux it tends to overestimate the magnitude of the radiative component, which is interesting. And so if I said these are the observations and this is the reanalysis, here's a question as well, which one is true? But there are reasons why we might not trust these observations as I showed in the previous plot. There tends to be disagreement between these plots, these data sets. But there is still a point of, do we solely trust this error 5 regression as our truth and make this conclusion that it's all variability and evaporation? Or are these observations suggesting that radiation tends to be a little bit more important? Either way, we still have the same conclusion that latent heating, evaporation dominates our heat gain.
It does look, Hamish, though, that the latent heat gain that's then transported is transported en masse. There doesn't seem to be as much partition into the other forms of loss. Is that what you see? Yeah, ERA5 has a big spike in the positive sense and then a smaller negative sense when it's transported.
Yeah.
All these other ones, or many of the other ones, look like they have the same magnitude positive spike as they do negative spike.
Yeah, and that's because these other components are higher, like you can see here, the
yeah.
sensible heat, which we know doesn't do much, is higher in our framer. So for whatever reason, there's a much, This blue is smaller because these other plots are higher.
Yeah.
So yeah, you're right there. It lowers that importance of the solar.
Yeah, okay, thanks.
And this is a regression, so a southward transport would be associated with a gain of a negative bump on the right-hand side of this anyway.
These could be reversed and interpreted in the same way, but I've shown it in the direction of the mean transport.
But that's what I'm saying, like that, the right-hand side of 30 north there, that's not necessarily a loss of latent heat by, it's not like you're gaining it on the left and then losing it on the right.
No, but the asymmetry is notable. And that was, you were saying all the energy that's transported is a function of latent heating.
But Dan has a good point. This is an anomaly. So it's anomalous positive. So we know that latent heating adds energy across the entire atmosphere. This negative anomaly just shows it's adding less energy poleward of that. So we're absorbing more energy by the atmosphere here, we're absorbing a bit less energy here. And that's what gives us that gradient of energy.
Okay.
But it's a regression.
Yes. What I'm saying is that suppose you have a southward transport of energy at for a given anomaly, you would see if latent heat flux is contributing to that southward transport, you would see a negative on the right-hand side of that.
Yeah,
is what I'm saying.
that's right.
It's not like you can say what's coming in on the left is going out on the right.
I gotta go talk to you about that, I don't understand.
Okay.
Yes, because it's a regression, you could reverse it and interpret it in a different way. But we can now plot this for the entire globe. So this takes a bit of time to get a hand of, but along this y-axis, as we have our heat transport anomaly, I'm showing the correlation here. So we're just back into the world of correlations. And then along our y-axis is the energy budget anomaly. So say we pick 30 degrees south and want to say where is the energy being gained and lost by the atmosphere that is consistent with heat transport across 30 south. And you can see this is for northward transport. So actually picking 30 north is easier here. So heat transport across here is associated with heat loss on this region and heat gain over this region. You can see there's a bit of a latitudinal extent, that we're not gaining energy in the southern hemisphere that's contributing to heat transport across to the north. It tends to be limited by a certain region. And now let's split it down into our terms. Here is our radiation, and this is really cool. You see the radiation only responds to heat transport. There's only a correlation. There's no correlation on the equatorward side. So radiation is not contributing to heat gain associated with polar transport. It only responds on the poleward side. And that's our thermal emission from more moving heat poleward, and it's emitting thermally on the poleward side of that anomaly. This is kind of where that discussion comes on before, that I'm showing northward transport, so it's in reverse for the southern hemisphere, but you could interpret the same thing. Southward transport is a loss of heat through that red there. Now that's true everywhere except the equator. Draw a line there. And this is where we do get a dipole of radiative forcing. So radiation responds on both sides to a heat transport across the ITCZ. So variability in rate of absorption does contribute to variability in heat transport in the tropics along the ITCZ, but not anywhere else in the globe. It's only a response to heat being sent across the latitude and then radiation response. I also have the regression coefficients just to show 0.5 watt per meter squared per standard deviation of heat transport, but so the correlation describes that same thing. So there's our radiation. We'll build this plot up for our terms. We can add our sensible and latent heating. Sensible heat does have a reasonable correlation, but the magnitude of sensible heating drops it down to really have a very small impact on the total budget. And this is where we get our latent heating absorption on the equatorward side of a heat transport anomaly. Equatorward side, on the order of, this is about 2 watts per meter squared in the zonal mean per standard deviation of heat transport going northward across that latitude. And lastly, I have got the tendency here, and this pops out in the polar regions. And so what we see here is that, say you pick the Arctic, if you've seen a lot of heat across 60 north, it's warming the moist static energy. It's increasing the moist static energy in your polar region by a lot. It's converging that heat transport and it warms that region. And so there's a very close correlation between your polar moist static energies and the polar heat flux across 60 north or 60 south. There's been a bunch of papers recently talking about heat waves in Antarctica and the Arctic and the importance of heat transport convergence, that it's not local terms that increase temperatures, it's your convergence of heat increasing your local moist static energy that leads to these heat waves in your polar regions. Now I can't finish this without showing some maps. Here's our spatial map of our 4 terms. Again, this is regressed onto the standardized heat transport across 30 degrees south. You can see there's very little, there's a little bit further north, but there's very little radiative absorption occurring for anomalous heat transport across 30 south. There's very little sensible heating. That's all additions to energy from evaporation that is adding to the atmosphere. And it's in certain regions as well. You can see it's confined to the ocean basins where evaporation tends to be largest, but it's also in a bit of a wave through the latitudes. And then on the poleward side, you can see we have these blues, losses of energy to our 4 components. So the blue here, a loss to tendency, shows that we're increasing the moist static energy of the atmosphere in these regions when we send more heat poleward. And so this is a regression on the monthly scale, and so from month to month, if you send more heat across this latitude, it tends to increase the moist static energy in these locations. It tends to warm the surface more through sensible heating in those locations, and it tends to emit more radiatively in those locations as well. There's a lot more to talk about here. There's a whole plot of dynamics that we could discuss of why we see this wave going through and the location of the ocean basins, but that's work for another day. We can look at the Arctic. This is interesting. You can see there the tendency pops out. So transport across 60 degrees north tends to be associated with increases in the moist static energy across the entire Arctic region. If you send more heat across 60 north, you tend to warm the full region, increase the energy. Our 2 surface budgets are only important over the ice-free regions, where you can have significant interactions with the ocean surface and either draw heat out or add more heat in. And we also have this radiative cooling across most of the Arctic region. Interestingly, the gain of energy tends to be the tendency. It's divergence of the moist static energy southward is what contributes most to poleward flow across that latitude. And now lastly, just the tropical plot. I've chosen 10 degrees north, so it's the one location where radiative absorption was important. As you can see here, it's absorption of more radiation along the equator and less radiation. It's a negative anomaly in radiation on the northward side of 10 degrees north. So this is associated with the ITCC shift to the south. So if you shift your ITCC south, you're going to send more heat northward. And so we have colder cloud tops, deep convection, and so we have more energy within our atmosphere due to radiation there. And we are emitting more radiation. You could also, you could think fewer clouds up here as well. So you're emitting from the surface, you have a greater radiative deficit by the atmosphere, and you get anomalous transport northward. We also see a cool evaporative trend going on. So relationship between heat transfer across 10 degrees north and evaporation in our eastern tropical Pacific. Of course, there's a lot more to discuss here, links to the ITCZ, links to ENSO. Yes, I thought I'd show the spatial map as well. So just before I finish up here, there's a bunch of future research questions that come out of this. The first one is the timescale of variance. So I showed this work for monthly variability in AHT, and I showed perhaps how unimportant radiation is for absorbing heat to be sent poleward, but this is on monthly scales. So the question is, when you jump up to annual scales or interannual scales, does radiation become more important? Yeah, that's a really big point there. Secondly, these dynamic associations. I've showed that evaporation is closely related to AHT variance, but what is causing that evaporation? We know surface winds tend to be what controls evaporation and heat transport out of the ocean through latent heating. What's causing those surface winds in those particular locations that is pulling heat out? There's a teleconnection question to ask. I'm showing this direct energy closure, but there's certainly a lot of discussion about teleconnections for this work as well. The representation of climate models, do models present the same results? Is even the mean state comparable? This work has been done. There's a lot of people out there who look at the climate model response and atmospheric heat transport, but it just sort of aligns with this work. And of course, improving our observing systems. Will future observing systems improve these results? Are we getting to a point where we can accurately observe surface turbulent heat fluxes? There are certain things in the works that might prove that viable, and is there a future where we can observe the global moisture energy throughout the entire atmosphere? At the moment we can't, but is there a point where we can do that? And now, just in the last few minutes, I do want to introduce a few of the exciting things I'm going on to do. We've just had this small campaign approved by the DOE arm. We've called it Shire. I've combined my few favorite things, Lord of the Rings, New Zealand, and infrared radiation. It's the Southern Hemisphere Polar Infrared Radiation Experiment. So I showed you before that radiation is really important in the mean state. Its variability is less important, but the mean state radiation is super important. And so we're sending some instruments down to Scott Base, the New Zealand-run base in Antarctica, later this year, and going into 2026. It's primarily an extended range area, which is managed by people further down in this building. That's it there, out on the front grass of that building. Going to do a bunch of cool radiation stuff, so keep your eyes out for the Shire that's going to be coming shortly. And then secondly, there's some very exciting work that I've been doing with Pre-Fire on satellite self-care and balancing data quality and quantity. So just as a shout out, as an advert, keep your eyes out for some of this work. It's going to be pretty exciting. Sometimes satellites also need a day off. They're not perfect. Okay, back to conclusions. I've shown that the Arctic thermal emission is responding to solar absorption. The Arctic is not. It's changing the budget of the Arctic region, but we've shown that we've shown for the Arctic that it's compensating nicely. I've shown that our observed surface energy budget severely underestimates tropical evaporation, and because of that, we underestimate how much heat is sent through the northern hemisphere in the mean state. But there is good agreement in the time series. And so let's take that time series and try to describe what is consistent, what energy components is consistent with variability in this time series. And I've shown that that tropical evaporation is very important for absorption of energy and the variance there. And that radiative absorption does not have a very big impact on the poleward flow of energy across 7 degrees north. I do want to thank all the people who have helped me along the way. Of course, Tristan Lequier for your work, and I really appreciate working in your lab. It's been a lot of fun. Aaron Donahoe, watching from Washington, has been an enthusiastic collaborator here. My committee, Liz, John, Dan, and Steve. Of course, the Pre-Fire team and the new Shire team developing in this building. the LitQA group. It's been a lot of fun. The office team that has evolved through the years. It's been a lot of very cool researchers I've got to share my space with. All the AOS faculty I've had the pleasure of being in class with. Pete, we wouldn't be here without you. Your work is indispensable. And Christy, Dee, Carolyn, and Scott, especially Christy and Dee for keeping me in the country. Even before I came here, they were doing a lot of things behind the scenes. I wasn't only aware of how much they do to keep me here. I really appreciate the work they've done. It's been a lot. Of course, all the graduate students, it's been a lot of fun over the last 4 years, and all my family friends in Madison and beyond. Here's me cheering with a cactus for you all. This work was funded under Fulbright, New Zealand, for the first 2 years of this work. That's really what got me here in the first place. And then beyond that, I've had funding from the NASA pre-fire news teams to continue on and finish up this work with Tristan. Here's a few photos. There's us in New Zealand in front of the rocket that launched pre-fire up to space. That's the Rocket Lab Electron rocket. All my friends and memories. It's been a lot of fun. Hopefully I can stay for a little bit longer before I have to get out of here. And of course the pets along the way. Thanks, Eddie. Okay, I'll leave it there. There's the conclusions. Any questions? We'll start with students first, move on to some faculty. Yeah, Ian.
Yeah, thanks, Hamish. So I came in a little late, I apologize. Maybe I missed something in the description of the budget. But I often fumble when I'm talking about heat transports myself, about the idea of latent heat release and also just the amount of moisture you have. So I guess what I'm asking is there, like, not all latent heat releases are created equal. So when you have heat transport, is the latent heat actually being realized, like the moisture in the MSE equation is being realized with a sensible heat? Or are there some events where it's simply just a movement of a bubble of moisture?
Yeah, so the bubble of moisture is accounted for by the transport of moistutic energy. And so I account for that by measuring the change of moistutic energy of both locations. So if it was just a bubble of moisture going from one point to another, it would be a drop of moistutic energy and an increase in moistutic energy, and no realized latent heat transport between the atmosphere and the ocean is the way to frame that. That this budget is considering the two surfaces that confine our atmosphere. And so if you do have a blob of moisture that moves across, it would be realized in a change in moistutic energy and the tendency. So that is being accounted for. Yeah.
So in those plots where you have the heat transport dipole across 30 south or 30 north, when I see blue on one side that's matching the dipole and I don't see blue on the other side, that's, if I understand correctly, that's moisture that's being converted into sensible heat on the other side of the dipole.
Yes, and that's why we don't see the latent heat on the other side, is because when you have an increased evaporation of moisture, it isn't entirely realized. So this is what they suggest the surface flux of latent heat is. Again, this is an anomaly space. So you have anomalous evaporation here, you have less evaporation here, is the first thing to interpret. But then this evaporation then condenses, you might have rain out, and then moisture not on the atmosphere, but you have that energy as dry static now. And that's why we can see losses through these other components. You can have sensible heating of the surface on the other side because you've converted that into dry static energy. Yeah.
Thank you very much.
If it was all just movement of moisture, you'd see this purple. It'll be purple here and purple here if it was just moisture that's going from here to here without transporting through your boundaries. Yeah.
Thank you.
Any others?
Yeah, going off that, I guess it's cool that you've kind of isolated latent heat as such an important term for the movement of energy. And you're saying radiation isn't important, but I wonder if all these other terms, like, because you're taking it out of the ocean, or if you did the same thing with oceanic heat transport, would you see the opposite? Because you're losing a ton of heat from the ocean, but not necessarily warming the atmosphere locally, and then you're warming the atmosphere somewhere else.
Yeah.
And so are all those other terms in the oceanic part of the total heat budget?
So yes, this blue component is a loss of energy from the ocean.
Mm-hmm.
So that's a good point. That this blue is telling us that the atmosphere tends to be warmed by the ocean. So the ocean is losing heat to the atmosphere, and then the atmosphere is adding heat back to the ocean is one way to interpret that, but this is an anomaly space. So you are introducing the opposite dipole in the ocean from this latent heat environment. Is one thing to show there.
Yeah, and I wonder if the other terms, if they will show up as more important on the ocean side versus the atmosphere.
The relative contribution from the atmosphere.
Yeah, because to get more latent, to get more heat out of the ocean has to be warmer. So was it warmed more by radiation at some point, and then that leaves? I don't.
Yeah. In my readings, I've found that it's very much wind speed is the big thing that controls evaporation from the ocean surface, and so it's not necessarily more heat that's being added to the ocean. It's we get more wind over the ocean. This might be the thing that causes more evaporation off the ocean. Shall we open up to any faculty now?
If you don't mind, could you go to your conclusion slide?
Sure.
Just a moment. I'll make sure I get this right. So in the upper right, this tropical evaporation soil and energetic component associated with atmospheric heat transport variance into mid-latitudes. Is it just into mid-latitudes, or is it also within mid-latitudes?
It's also within mid-latitude.
Okay, so I'm wondering, there's been some studies that have suggested that a significant part of heat transport northward, both atmosphere and ocean, is generated by, say, tropical cyclones in the ocean, by a lot of mixing, and that helps the oceanic transport. But I'm curious if the evaporation associated with either cold surges into very low latitudes or tropical cyclones themselves, I'm just trying to look for a dynamical link between what's happening in the tropics. Is that a communication of energy from the tropics into mid-latitudes, and that's where you're seeing the increase in variability with mid-latitude cyclones?
Really good point. You can see, it's a good way to show this, like the extent of latent heating on the equatorward side goes from 20 degrees, about 20 degrees up to 60 degrees.
Right.
So up until 60 degrees north, the evaporation of the ocean surface is still important on the equatorward side of a poleward flow anomaly. So it's across the entire mid-latitudes and then into it maximizes at 30 degrees, that's why I chose that line. The magnitude and the correlation, that's about a 0.67 correlation there, and it's a few watts per meter squared. That's why I chose it, but there's an interesting point that there must be, we know there's different dynamics in these two different regions, and so is it tropical cyclones here and then it hands over to something else here, or is it tropical cyclones across the entire extent that causes variability? I think that's a really cool question to ask.
You said you broke this down by months, right?
Yes, monthly.
Do you see, how does that picture change from, let's say, July or August into the winter?
Yeah, I haven't done this correlation for single seasons, but that'd be interesting to see. We know the magnitude of heat transport reduces right down in the summertime, and so I'd imagine we'd see, if the magnitude of the transport reduces, does the relationship stay the same? I don't know if that's true. And we know there's different things going on in each season that might change what this picture looks like.
Thank you.
Along those lines, if over 11 years of data, couldn't you just pick out the days within certain months in which a tropical cyclone was in the Atlantic or Pacific Basin and composite those and then do your analysis just to maybe test this question?
Yeah, and that's really something that I do want to dive into further is the anomalous heat transport caused by a single event? Is it a single event in a month that's causing this big flow of heat forward anomalous to what it usually is? What the literature tends to say is that it's our large scale, it's our planetary waves, and when the planetary waves align with a moist-taking energy anomaly, that's the description of what causes things. So it's not, they say it's not the synoptic scale, it's not variability from day to day.
Everybody says
Yeah.
that. They default to that, and that might not be right. I mean, I don't know the literature, I'm kind of joking, but it would be, you could probably test it.
Yeah.
Because it seems to me it's equally a priori, without any knowledge, logical that if you have an extreme event, that can reshape the large-scale flow. It doesn't need the large-scale flow to already be ready to receive it.
And there's plenty of examples out there of an individual event adding so much energy to Antarctica that has increased the monthly mean.
Yeah, that'd be really interesting.
Yeah. Be a very good thing to go into. Till.
Slightly different question. First, wonderful presentation. I see why you won your award.
Yeah.
But, and I may have asked you this before, how are the analyses, the reanalyses, fully independent of the observations?
No.
And might that impact why your performance increases as you go? into the more recent.
Yes, that's
Yes.
a really good point there. I could go back to that time series of why we get better agreement between the products. And we know that our observation systems are getting better over time. And so, is this the kind of idea that you're thinking about? Like, why is there so much more error back here?
Yeah.
Like, there has been many different satellites launched over this period, and different things get ingested in different ways over time between reanalysis and observation.
And
So-
do the C-flux and OA flux also get used in Era 5?
The satellites that get used for these are used in Era 5. It's the scalerometers, it's sea surface temperature, it's surface wind speed, it's all those fundamental aspects that these reanalyses do ingest. And so, yeah, we don't have independence, which makes it even more interesting that they diverge in such a way that the physics that's going on here produces a heat transfer that's different to what solely from observations suggest. Yeah. Time for one more question. We're just after the hour, but we'll go back. Hitchman?
Yeah, sorry, I can come in as well, but do you have a theory for or did you already discuss the meridian pathway for those correlation patterns, maybe a few hundred kilometers? Is that a synoptic scale transport characteristic scale, or how would you?
Yeah. It's a really interesting point, and it's consistent sort of across all latitudes until you get into your poles when your tendency becomes important. But yeah, there's a limit to how far our forcing is. So like, let's pick 30 degrees south. Heat transport to 30 degrees south is not associated with Antarctic energy budget anomalies. There's an extent to how important energy budget is to a 30 degrees south transport. And so heat anomalies at the equator has no association with heat transport across 30 degrees south is another way to interpret that. So there is an extent, and it tends to be within 30 degrees across the entire planet of how important a local energy budget anomaly is to a heat transport anomaly. Yeah, and maybe that is related to the synoptic scale of how large can a storm influence on the ocean surface. Yeah, I haven't seen this discussed much, and so I think it's interesting to find this meridional scale of heat transport. And yeah, the point of teleconnections come into play. It's like, so is the energy budget over Antarctica not important for heat transport here, or we know there are other things that control teleconnections rather than the direct energy contributions, but it's just cool to see that within a month, the regression of these budgets does have a meridional extent. Yeah, Rudra.
I had one quick follow-up question on that. You mentioned that you regress the time series. Have you tried any lead and lag for the same? Because
Yes.
there might be a lag.
So I do have a supplementary figure for this. I plotted the autocorrelation just to show, here it is here, that in the mid-latitudes, AHT does not have an autocorrelation beyond 1 month. In the tropics, there tends to be memory, so there is substantial autocorrelation out to 4 or 6 months, depending on what reanalysis you use. So in the tropics, if you have a heat transport anomaly, it tends to persist for a few months, probably associated with things like ENSO and large-scale tropical systems. But in the mid-latitudes, there is no correlation from 1 month to the next. So this is going back to maybe John's idea that it's a single storm or a single few extreme events within a month that don't persist for other months, that cause a heat transport anomaly. So there is no autocorrelation through your mid-latitudes there. So yes, I wouldn't expect, because of that, it tends to be within a month. So the idea of going smaller scale, and so Tyler Cox, who I showed, he did daily scale heat transport anomalies as his PhD, so he'll be a person to ask about that to dive into that further. Cool, past the hour, let's wrap that up. Thank you all for coming.